In the last video, we took a look at double slit interference and saw how the difference in path lengths contributes to an interference pattern. We can see the same thing in a Michelson Interferometer. We've already encountered the Michelson Interferometer when we were discussing the Michelson-Morley experiment during our explorations of special relativity. The idea goes like this. You have a coherent light source. Nowadays you'd use a laser. It's much easier to do than the way Michelson-Morley actually did it. You shine the laser beam onto a beam splitter, which is just a fancy term for a partially silvered mirror. This beam splitter will allow some of the light to pass through, and it'll reflect off of this mirror here. And then that light goes back. When it gets to the beam splitter, some of the light will pass through and strike the laser. We don't really care about that except to use it to help align the optics. And some of it will bounce onto the screen. Also, some of the light here bounced off the beam splitter, struck this mirror, bounced back. Then it would strike the beam splitter again. Some of it would bounce back down onto the entrance aperture of the laser, which again we use just to align things, but some of the rest of it would pass on through. These two different bits of light that got split off by the beam splitter, when they combine at the screen, will interfere. And what's going to determine whether this interference is constructive or destructive at the center of the interference pattern is the difference in the round trip distance that each bit of light makes. So if I want constructive interference, then what I'm going to need is this round trip distance, 2L1, minus this round trip distance, 2L2. Actually, let me swap them. Not that matters. I'm going to put an absolute value anyway. I need this round trip distance to be equal to some integer number of wavelengths. So I can pull a 2 out of this. 2L2 minus L1 equals m lambda. So I'll have constructive interference if L2 minus L1 equals m lambda over 2. There are fun applications for this. For instance, indices of refraction for gases are often measured by observing the interference pattern. Then you stick a gas cell with an unknown gas in this area right here. Because the gas has a higher index of refraction than air, that will cause a change in the number of wavelengths in this part of the round trip. You can observe the change in the interference pattern on the screen, and from that you can deduce the index of refraction of the gas in the cell you put over here. The pattern isn't just a single dot either. So let's say you have constructive interference in the middle of the pattern. If you look onto the screen, in that case you would have a bright dot in the middle. However, the light that doesn't hit perfectly on axis is going to be taking slightly longer trips than the light that was perfectly on axis. And same with the off-axis light coming off the mirror, passing through the beam splitter and hitting off the mirror over here. So as a result, the pattern you get looks kind of like a target where you're going to have alternating bright and dark rings. But usually, in a lot of applications, what you do is you adjust the distance L2 by turning a screw or something like that. And what you'll do is you'll see an oscillation between constructive and destructive interference. This is especially common if you're using this to measure the wavelength of the light you're looking at. So, okay. Now, this is going to seem like a bit of a hard segue here, but it is going to tie back together a little bit. We're going to work off of this idea of differences in round trip distances to also look at thin film interference. However, with thin film interference, there's one additional complication that we have to take a look at. And to that end, I'm going to introduce an experiment known as Lloyd's mirror. L-L-O-Y-D, Lloyd's mirror. So in Lloyd's mirror experiment, what you do is you have yourself a mirror, like so. And you set up a screen at the end of the mirror. And then, and here's the tricky bit, you set a slit light source very close to the mirror. Now the thing is that there will be light that goes directly from the source to some point on the screen, and there will be light that bounced off the mirror to hit the screen. And that light will be as if it came from the, let's draw the image a little better. So this is our virtual image of our source. And it'll look like the light came from the virtual image. Now, of course, what really happened is, following the law of reflection, the light bounced off the mirror. So you got light coming from the same source interfering with the screen, taking two different paths. But if you think about it, in a very real sense, to the screen, it's as if you have this light source here and you have this virtual image source here. So to the screen, it basically looks like the same difference as Young's double slit experiment. Except one really weird difference happens. That difference is that everywhere in Young's experiment, you see a bright fringe, you see a dark fringe in Lloyd's mirror. And everywhere you see a dark fringe in Young's experiment, you see a bright fringe in Lloyd's mirror. Now, what I would like you to do here is I want you to think about this and think about what this experiment is telling us what's happening when light bounces off a mirror. So pause the video and we'll get back together. Okay, so since the only thing that changed, between relative to the screen is that the light from the virtual image really bounced off of here. To switch bright and dark completely means that the act of the light bouncing off the mirror had to somehow change the phase of the light by 180 degrees. So that means if you had a crest of light hitting the mirror, it reflects back as a trough. If you have a trough of light hitting the mirror, it reflects back as a crest. You've seen this sort of thing before. If we think back to a mechanical wave, if I were to have a surface here, and let's say this is a nice firm surface like this. I have a string, I send a pulse down the string like so. When it reflects back, that pulse reflects back upside down. Similar, and then just for comparison's sake, if you had a string that was, say, attached, to a ring that was free to slide up and down a rod or something like that, then, when the pulse comes in, we can draw it better. Maybe not. Then when the pulse comes in, it reflects back out, right side up. And you can even see this sort of an effect, say, if you had a wave that was going down a string, and then you get to an area where, say, the material in the string is denser or something like that, you would be going to an area where the wave speed was higher to where the wave speed was lower. So in that example here, we can say have a thin string under tension that gets attached to a thicker string under tension. And if we send a pulse down, what will happen is when it gets here, this bit, some of the wave will continue to propagate forward, but you'll get a pulse that reflects back upside down. So, and if you reverse, so this is where the wave speed is high. And if you were to reverse this, so say this was the thicker string here, going to a bit of thinner string. So the wave speed is slower in the incident medium. Then what will happen is the pulse comes in, the transmitted pulse will still go through right side up, but here now the reflected pulse will also come back right side up. So we've seen this with mechanical waves. It turns out it's the same deal with light. And the usual sort of notation I like to use is, let's say this is my surface here. This is N1, this is N2, and let's say we are going from a low to a high index, so N2 here is greater than N1. In this notation here, what I like doing, saying, okay, we'll have some light that goes through refracted, like so. Then for the reflected light, what I like to do is draw a dotted line. And that dotted line should be read as that there was a 180-degree phase change. So it's the same deal. Light was going faster in medium 1. It goes slower in medium 2. If the light wave bounces off the slower medium, it reflects back inverted, just like with a mechanical wave on a string. Okay. On the other hand, if my N2 is less than my N1, so the speed of the wave is higher in medium 2, we'll still have our ray coming in. We'll still have a ray that gets refracted through. And then for the light that gets reflected out, I just usually draw a solid line so that I can keep straight that there was no phase change. Okay. So this leads to two cases for thin film interference. So what I like to call case 1. So in thin film interference now, what as the name implies. You have a thin film that's sitting on top of some surface. So for instance here, we could have it be that this is my highest index, then this bit right here, N2, will be a lower index than N1. And then to finish it out, we could have that N3 is less than N2, like so. Now, if the light is coming in nearly vertical, so I'll just draw it as vertical. If the light's coming in as vertical, some of the light will pass through, like so, and some of it will get reflected. And I'm just going to draw the ray parallel in order to disambiguate it. Whoops, I'm sorry. And because it's bouncing off of a lower index, there would be no phase change. And then this light here, pardon me, I'm just going to displace it over to the side to make that reflection more obvious, would reflect back up here. So let's go ahead and say the thickness of the film is T. So here we have 0 phase changes. This is one example of case 1. So then to decide whether or not the light that comes in will happen, some of it will pass through, reflect back off of the surface, and some will continue to pass through here, but I'm ignoring that for the moment. So the light that reflects back will be interfering with the light that had already reflected earlier on the surface. So if we're going to have constructive interference, this is just like the Michelson Interferometer. We need to worry about this extra round trip distance right here in the thin film. The light that passed through to hit the bottom of the thin film and then comes back up, the extra round trip distance it made was 2T, where T is the thickness of the film. If we're going to have constructive interference, I need this round trip distance to be some integer, I'll call that integer m, times the wavelength in this medium right here. Well, the wavelength in medium 2 is the wavelength in a vacuum divided by N2. And similarly for destructive interference, so if my round trip is 1, 2, 3, 4, 5, 6 wavelengths in the film, I'll have constructive interference. For destructive interference, now the round trip distance will need to be 1/2, 1.5, 2.5, so forth, wavelengths in the medium. So it'll again be the wavelength in the vacuum divided by N2. Okay. It also turns out that case 1 works out if there are 2 phase changes. So for instance here, let's say you have a thin film of water on glass. We'll show an example of this in a moment. So here, the ray would come in. Some of it would reflect off of the surface, but when it does, there would be a 180-degree phase change. And similarly for the light that reflected off the bottom here, there would also be a 180-degree phase change. And then again, light will still continue to pass on through, but I'm ignoring that for the moment. So here, where N1 is less than N2, is less than N3, so for instance, a water slick on glass, water has an index of typically about 4/3, glass about 3/2. At both surfaces, the light coming back up will have a 180-degree phase change. Well, if they both change, then it's like neither of them changed. And so you wind up having the exact same results. But I should point out, the results can be quite pretty. Pardon me a moment here. There it is. So here is a picture I took. I had placed, I was at a rest area. I had thought I had dumped all the ice cubes away in the proper place when I was emptying out my drink. One of them ended up on the roof of my car. Now my car happens to have a glass roof. So when I came back from the rest area, the water underneath the glass underneath the ice, between the ice and the glass, had started to melt, and it created a thin layer of water sitting on the glass. The light coming in from the sun has all wavelengths of light. So in the middle area where the water was sitting on the fattest part, where the ice cube was sitting on the fattest part of the melted water, the longest wavelengths of light could fit nicely into a round trip, and so you see the nice reds. As you look way out to the edge in the photo here, here the water was thinner because the puddle was reaching out past the ice cube and was thinning out. And because it was thinning out there, the wavelengths that would fit in for a round trip distance were the shorter wavelengths, and so tending towards the blues. So as the thickness of the water varied across, you wound up picking up all the different pretty colors. Add to that some refraction from the ice cube, and I think the result was pretty darn pretty. Okay, so back to our thin film interference, and we'll get to some more applications in a second. The other possibility is what I like to call case 2. So in a case 2 situation, again, there are two ways it can happen. One way would be, say, if your film happens to have a lower index than the surroundings. So if this is N1, N2 is less than N1, and N3 is greater than N2. So in a case like that, we'll still have our incident ray coming in. Some of it will pass through. Again, light will continue to pass through to the other side. But for the light that bounces off the upper surface, there will be no phase change because it's bouncing off a lower index. For the light that bounces off the lower surface, however, there will be a 180-degree phase change. So if I want so this is one phase change. So if you want constructive interference, here for my round trip distance, if I say the thickness of my film is T, now instead of it being an integer number of wavelengths, because only one of them has a 180-degree phase change, it's as if one of them had a half wavelength head start already. So then to make up for that half wavelength head start, now the round trip distance needs to be a half, 1.5, 2.5, whatever, times the wavelength in the film. And for destructive, you need it to be m lambda over n, because you want an integer number of wavelengths, and then the fact that one of them had 180-degree phase change will give you your destructive interference and make that color of light not reflect back, but only pass through. More on that in a moment. So if you want, you can try to make this. It's kind of hard with modern microscope slides, but you can still try. If you take a couple of pieces of microscope slide and you put them really close to each other, I find using like onion skin paper or something like that between them, you can make an air gap that is sufficiently thin that you can try to do this. But for some reason, I find that the newer construction slides versus like the really old ones that might be sitting in the back of some stockroom somewhere, I don't have as much luck with them. Maybe it's just because they're sharper and I don't like handling them as much. But anyway, you can try it. One that's easier to do, to give you a case too, though, is the opposite situation, where the index in the middle is thicker, is higher, sorry, than the surrounding indices. So this would correspond to, for instance, a soap bubble, the film of the soap bubble, or even though gasoline is less dense than water, it turns out to have a higher index of refraction than water. So because it's lower density, if you go out into a parking lot after a rainstorm, you'll get a thin film of gasoline on top of the water puddles that are left behind after the storm is over. Because it's lower density, it'll float to the top. However, it turns out I still have a higher index of refraction because of the details of the molecular structure. Either way, what winds up happening here is the light that bounces off the upper surface is the one that changes phase, and the light that bounces off the lower surface does not. So we're just changing who gets the head start, but the results are the same. So either way. Now, if you want, so design for constructive interference is a thing that you can do. And sometimes that's an intentional effect that you want. For instance, if you pull out relatively recent US currency and you go look at the number in the, for a $10 bill or higher, you go look at the number in the lower right hand corner, you can, if you tilt it back and forth, you'll see that it changes colors. And what's happening is when you look directly above it, you're getting some sort of constructive interference. When you start looking at it sideways, you'll select for a different wavelength because now the round trip distance will be at an angle, so there'll be extra distance covered in the thin film. So you wind up selecting for a different wavelength. I suspect this is what's behind the color shifting ink that the Bureau of Engraving and Printing uses. However, they are not discussing it publicly, at least with anyone like me. Sometimes, though, what you really, really, really want is destructive interference. And so this example here, if you happen to have your cell phone lying around, go flip it around and take a look at the camera lens. Likely, the camera lens is either going to have a green hue, sort of a bluish hue to it, or a reddish hue to it. And that turns out that it's because there are coatings put on the lens, actually a whole birthday cake arrangement of coatings of different indices, but there's a whole bunch of thin films put on the lens that are designed to create as much destructive interference over as many wavelengths as possible. Now, why would you want to do that? Well, if you have destructive interference, then that means that that light isn't getting reflected back, but it has to go somewhere, and the somewhere it goes is forward, deeper into the camera system. Now, the reason why you see some color is because usually you can't make these things perfect. You can't get destructive interference across the whole light spectrum practically, so the lens designers choose to pass through the colors that the sensors need the most help detecting in the camera. So okay. With that, I think we are good, and I will catch you all in the next one. Have a good one.